Let's look at this question. A particle of mass m moves in the one-dimensional potential Vx equals to minus alpha by 3 x cube plus beta by 4 x to the power 4, where both alpha beta are positive quantities. One of the equilibrium point is x equals to 0. The angular frequency of small oscillations about the other equilibrium point is option A 2 alpha by square root of 3 m beta, option B alpha upon square root of m beta, option C alpha upon square root of 12 m beta, and option D alpha by square root of 24 m beta. So in this question we have given a one-dimensional potential Vx and whose one of the equilibrium point is x equals to 0, and we need to calculate the angular frequency about the other equilibrium point. For your convenience, I have also drawn this potential in a graph. You can see this graph has a maxima somewhere around positive x-axis, which we will calculate. So to find this equilibrium point, we will equate the first derivative of the potential with respect to the position and put it equal to 0. Setting the derivative, setting the first derivative of this potential, which is minus alpha x square plus beta x cube to be 0, we get our equilibrium position x naught to be 0 and alpha by beta. Now we have already given this information that one of the equilibrium point is x, but the question is asking we need to calculate the angular frequency about the other point, which is alpha by beta. Now we will calculate the second derivative of this potential, which comes out to be minus 2 alpha x plus 3 beta x square. Now putting the value of other equilibrium point alpha by beta, the value of second derivative about this equilibrium point comes out to be alpha square by beta, which is a positive quantity, which suggests that this equilibrium point alpha by beta corresponds to a minima. So it is a stable equilibrium point, and around this equilibrium point the oscillations are possible. Now we know the formula of angular frequency, which is square root of k by m, where k, the spring constant, is the second derivative of the potential around the equilibrium point. Putting the value of k around alpha by beta, which we calculated to be alpha square by beta, and putting it in the formula, we get omega equal to alpha by square root of m beta. So the correct option is option B, alpha by root m beta.